Now we will see what is Coulombs law. Okay, in electrostatics, consider two charges Q1 and Q2 separated by a distance r. Okay, what is, we have seen two like charges repel each other, two unlike charges attract each other. Okay, what is that amount of attraction force or repulsion force? We want to see the force between two charges Q1 and Q2 is found to be, this is an experimentally stated law. Okay, not a derived one. There is no derivation for Coulombs law. Okay, it has been experimentally observed and stated. Okay, that force is found to be proportional to the product of two charges Q1 and Q2 and found to be inversely proportional to square of the distance between two charges. That is, the Coulomb force of attraction or repulsion between two charges is proportional to Q1 Q2 and proportional to 1 by r square. So F is proportional to Q1 Q2 by r square, we write. That is, F equal to, remove this proportionality sign and put a constant k here. It is k Q1 Q2 by r square. Okay, that is Coulombs law or electrostatic force of attraction or repulsion is an inverse square law force. Remember that point will be useful in future. Okay, it is an inverse square law force, and that force is always acting along the line joining the two charges. Means the force of attraction or repulsion between these two charges will be either in this direction or in this direction. Similarly, the force on this charge due to this one will be either like this or like this. That is, the electrostatic force of attraction not only depends on the distance between the two charges but always acts along the line joining the two charges. That is, okay, in another way we can write this force as a function of r. It depends on the distance between the two charges and always acts along the line joining the two forces. That is, this can be simply represented as capital F equal to F of r into r cap. Such force is known as a central force. Such force is known as a central force. The central force property of electrostatic force, okay, right, will become very useful in future for us. Okay, it is known as a central force. A central force is represented like this. Central force is what? That central force should always act along the line joining the two charges or two particles, and it should depend on the distance between the two charges. Okay, next one, right, this k value is found to be experimentally found to be equal to, right, 8.99, very close to 8.99 into 10 to the power, right, 9, 10 to the power 9 Newton meter square per Coulomb square. Okay, k is experimentally found to be close to, or in solving problems you can take this as 9 into 10 to the power 9 Newton meter square per Coulomb square. This constant k is equal to, right, 9 into 10 to the power 9 Newton meter square per Coulomb square. Okay, now this is the magnitude of the force. What is the direction of the force? I have told you direction will be in the along the line joining the two forces. Okay, now in vector notation this can be represented like this. In vector notation this can be written like this with direction F bar equal to, right, k into Q1 Q2 by, right, r cube into r bar, you can write. Okay, r bar, where r bar is the position vector of the force experiencing particle with respect to the force exerting particle. Okay, r bar is the position vector. Suppose say, right, one charge Q1 is here, another charge Q2 is here, Q2 is here. Okay, right, suppose what is the force on Q2 due to this Q1? Okay, it is the position vector of the force experiencing particle with respect to the force exerting particle. Means the position vector of Q2 with respect to Q1, if I write it as r bar, okay, F bar equal to k Q1 Q2 r bar by r cube. R bar by r cube. Okay, right, now suppose say if the position vectors of individual charges are also given with respect to some coordinate system like this. Suppose say Q1 position vector with respect to the origin is r1 bar, say. Okay, Q2 position vector with respect to, right, the origin is, suppose say r2 bar. R2 bar. Okay, now what is the force in magnitude as well as in direction? Force experienced by Q2 by Q1. Okay, what is the force acting on Q2, right, by the force Q1 if you want. Okay, position vector of Q2 with respect to Q1 is nothing but R2 bar minus R1 bar. Okay, that is F bar equal to, okay, K into Q1 Q2 by what is the position vector of what you call Q2 with respect to Q1? It is R2 minus R1. So R2 bar minus R1 bar by R2 minus R1 magnitude Q. Okay, now what is the force experience? What is the force acting on Q1 due to Q2? Force experienced, okay, I'll write force on Q2 due to Q1, I'll write it as F2. Force acting on Q1 due to this charge Q2, okay, that is, I'll write force on Q1, I'll write it as F1. F1 bar equal to K into Q1 Q2, right, into what is the position vector of Q1 with respect to Q2? R1 bar minus R2 bar, okay, that is R1 bar minus R2 bar by R1 minus R2, okay, whole cube. R1 minus R2 whole cube. Okay, like this. If position vector, what is position vectors R1, R2 here? R1 is nothing but, right, x1 I cap plus y1 j cap plus k1 k cap, sorry, xy z1 k cap. Similarly, R2 will be equal to x2 I cap plus y2 j cap plus z2 k cap. If position vectors of two particles charges are given like that, okay, between 2 point charges, right, the forces on with direction will come across. We will come across the force with directions from this formula. Okay, now what are the properties of these forces? We have seen it is a central force, that is, it depends on the distance between the 2 point charges and also acts always along the line joining those two charges. Let it be attraction or repulsion. Okay, right, next one. This force is conservative in nature. Okay, electrostatic force is a conservative force. Remember, that's another important point. Okay, in electromagnetic theory, as we go further deeper into these topics in EM theory, these things will become very important. Okay, next properties. Electrostatic force is conservative in nature. Okay, conservative in nature. Conservative in nature at this stage. Remember, what is a conservative force field? In a conservative force field, work done around a closed path is always zero. Okay, let us remember it that way at this stage. As we go deeper into the topic, things will become more clear. Okay, electrostatic force is conservative force. That is, work done around any closed path. Work done around any closed path will always be equal to zero. Okay, that is another property of electrostatic force. Okay, next one. This electrostatic force or Coulomb force, right, obeys what is known as superposition principle. Okay, superposition principle is one of the most important principles in physics. Okay, superposition principle is applied in most of the cases. Okay, right, in quantum mechanics we come across, in waves we come across, in optics we come across, in electrostatics, in EM theory. Okay, many places we'll come across that superposition principle. Okay, electrostatic force obeys superposition principle. Superposition principle. Okay, what is that superposition principle? If suppose say there is one charge Q and there are two other charges Q1 here, Q2 here. Okay, this Q1 is also exerting, right, force on Q. I'll call it as F1. Q2 is also exerting some electrostatic force on Q. I'll call it as Q2. When two charges are simultaneously exerting a force on a third charge, what is the resultant force? Resultant force on this charge Q is nothing but the vector sum of the forces due to individual charges. What is the force due to Q1 on Q? Okay, individual force is F1. What is the force on Q due to Q2? It is individual force F2. What is the resultant of these two forces? Resultant of these two forces is vector sum of these two forces F1 and F2. That is, if F1 bar, superposition principle says what? If two or more charges are simultaneously acting, on a third charge Q, the resultant force is the vector sum of the forces due to individual charges. That is, resultant force F bar equal to F1 bar plus F2 bar plus F3 bar plus etc etc. We write it. What is true for two charges will be true for n number of charges, or given some charge distributions also, whatever it is. Okay, this is called superposition principle. Okay, if there are two forces, what is a vector addition? How do we if two vectors are there, F1 bar and F2 bar, what is the resultant force direction? Resultant is F bar equal to root of F1 square plus F2 square plus 2 F1 F2 cos theta. Okay, where theta is the angle between F1 and F2. Resultant of two vectors is found like this. How about resultant of three vectors? Find the resultant due to these two, then add that resultant to this one using the same formula. You can extend this process to anyone, or you split each vector into, in vector analysis you must have learned, into x components and y components. Add all x components algebraically, all y components algebraically. That way also you can find out resultant force. Okay, right? So resultant force, the force is conservative in nature. The force obeys superposition principle, that is, the resultant force is vector addition of all individual forces. This is another aspect. Next one, this is an electrostatic force is an action reaction force pair. Okay, in some of the exams the question will come, which of the following are action reaction pairs? Okay, electrostatic force is an action reaction pair. Okay, that is, if there is one charge q1 here, there is one charge q2 here. Okay, what is the force of attraction or repulsion between these two charges? Okay, k, right, k q1 q2 by r square, right? That gives you magnitude. Now force experienced by q1, sorry, force experienced by q1 due to q2, right, is like this. Okay, both are positive charges. Force experienced by q2 due to q1, say it is acting like this. Okay, both are equal in magnitude and opposite in directions. Okay, this particle exerts, this charge exerts a force on that charge exerts a force on this charge, right? Two equal and opposite forces. Okay, this is called an action reaction pair. This is called an action reaction pair. Okay, right? Now, sorry. Now, suppose say force on q2 is, suppose say 2i minus 3j in vector notation. Okay, force on q2 due to q1 is in the direction 2i, or is given by 2i minus 3j. What is the force on q1 due to q2? Okay, opposite, equal and opposite it should be. Okay, that is, right, the force experienced by this charge will be minus 2i plus 3j. Minus 2i plus 3j means this force will be exactly in opposite direction and equal in magnitude, right, with respect to this force. If this is 2i minus 3j, force experienced by q2 because of q1, if it is 2i minus 3j, force experienced by q1 because of q2 will be minus 2i plus 3j. This is the meaning of action reaction pair. Okay, so these are some aspects of the electrostatic force. Now here, how are we writing? What is this constant k? This constant k is nothing but, is simply written as, in SI units we write this like this. Okay, F equal to k q1 q2 by r square. K is experimentally found to be, right, nearly equal to 9 into 10 to the power 9, right, Newton square per Newton meter square per Coulomb square. Newton meter square per Coulomb square. Okay, Newton meter square per Coulomb square. Now, usually K is conveniently written as 1 by 4 pi epsilon naught. What is this K? When you want the problem to be solved in SI units, when we are using SI units, K is conveniently written as 1 by 4 pi epsilon naught. Okay, where epsilon naught is called permittivity of free space. Okay, permittivity of free space or vacuum. Permittivity of free space. Epsilon naught value is 8.85 into 10 to the power minus 12 meter square Coulomb square per Newton, or simply Farad per meter. Simply Farad per meter. Okay, 8.85 into 10 to the power minus 12. This is called permittivity of free space. Okay, this K is written as usually 1 by 4 pi epsilon. It becomes very convenient. Here it may look slightly complicated, but when we go deeper into electrostatics and electromagnetic theory, if I simply take it as K here, everywhere we have to keep on dividing most of the relations with 4 pi epsilon. So okay, in order to simplify things at higher levels, here we are writing K as 1 by 4 pi epsilon naught. Remember, some fundamental aspects of physics are slightly complicated. They are taught at advanced levels. Okay, right? Though some things are very fundamental, you'll start studying them in +2 level. Okay, but why you are studying like that, why things are going in the way you are writing, you'll understand only when you pursue the subject at master's level. Simply one example: why energy should be conserved, why energy should be conserved, why linear momentum should be conserved, why charge should be conserved. Okay, these are all fundamental questions. Okay, what is mass, what is charge, what is spin, etc. Right? When do you understand? Not at +2 level, not at your BSc graduation level. Okay, you go to advanced level like masters, you study why momentum is conserved, or how momentum is getting conserved in nature, how energy is getting conserved, what is the concept of time, etc. Things are learnt at advanced levels. For now, at this +2 level or graduation level, okay, simply we learn how to write that sum. Okay, so K is usually written, right, as 1/4 pi epsilon naught, where epsilon naught is called permittivity of free space, 8.85 into 10 to the power minus 12 meter square Coulomb square per Newton, or simply Farad per meter. This is when the two charges are present in vacuum. When Q1 and Q2 charges are point charges are present in vacuum, okay, the force between, suppose say they are present in some dielectric medium like air or any other dielectric, glass or something like that. In any dielectric medium, the force is written as F equal to, right, 1/4 pi epsilon naught into K Q1 Q2 by R square. Force is written as, okay, 1/4 pi epsilon naught K into Q1 Q2 by R square. K is some property of the dielectric medium called dielectric constant. Okay, dielectric constant. Okay, or relative permittivity also. Okay, relative permittivity we call. Relative permittivity or dielectric constant. Right, now I'll write this point as, this can be simplified as epsilon naught K. Epsilon naught K. This K is called dielectric constant, or it is also known as relative permittivity. We can write it as epsilon naught into epsilon R also. K or epsilon R, both are one and the same thing. Both are one and the same thing. Okay, dielectric constant or relative permittivity is usually denoted as epsilon. This is called absolute permeability of that medium. Absolute permeability of that medium. Absolute permeability of the medium. K equal to epsilon naught, epsilon R, or epsilon K. So the resultant force in any dielectric medium becomes 1/4 pi epsilon, right, Q1 Q2 by R square. That is, the Coulomb's electrostatic force of attraction or repulsion depends on the medium in which those two charges present also. Okay, the medium in which the two charges are present. Okay, this is 1/4 pi epsilon naught, where epsilon equal to this whole thing. Okay, so this is about the Coulomb's law. Okay, and we will see some problems based on this Coulomb's law. Okay, different charge distributions, what is the force on that charge due to this charge, etc. we will see now. Okay, now we will solve some simple problems using Coulomb's law. Okay, now the problem is, there is an equilateral triangle. Okay, three identical charges, each Q, are placed on the three vertices of an equilateral triangle of side A. Okay, find the magnitude of the net force on any one charge. Net force on a magnitude of net force of any one charge. Okay, now the situation is like this. Now we will consider a triangle here. Okay, of side A, three identical charges are on the three vertices of this triangle. Okay, I'll call this as what you call corner 1, corner 2, corner 3. Now what is the magnitude of the net force on any one charge due to the other two? Okay, so force on, I'll call this as corner 1. Okay, the force on this charge due to this charge, it will be like this. Okay, I'll call it as F1, means force on charge Q due to the charge on corner 1. Similarly, force on charge Q due to the charge on corner 2, that force direction will be like this. I'll call that force as F2. Okay, force on this charge Q due to the charge on corner 2. Okay, what is F1? Now this identical charges, so F1 is equal to, right, 1 by 4 plus 1 or simply K into Q1, Q2, both are Q and Q only, so Q square by, the distance between them is A, it will be Q square by A square. Okay, similarly, force F2 due to this charge on corner 2 on this Q is F2 equal to, again constant K only. Okay, here also the two charges are equal, Q square by, distance between them is A only, so A square. Okay, so F1 is like this, F2 is like this. Okay, what is, now we have to find out the resultant of these two forces. Okay, force is a vector quantity, so it is a vector addition of two vectors. Now what is the angle between these two forces? In an equilateral triangle, all three sides are 60, 60, 60. So if this angle is 60 degrees, this angle also will be 60 degrees. So resultant force, resultant of these two forces, F equal to root of F1 square plus F2 square plus 2 F1 F2 cos 60 degrees it will be. Okay, F1 square, F2 square, both are equal in magnitudes, remember. Okay, that is, I'll simply write it as F square plus F square is nothing but 2F square plus here also F and F are equal, 2F square. What is cos 60? Cos 60 is half, so into half. Like this 2 and this 2 gets cancelled. Okay, 2F square plus F square it is. Okay, nothing but 3F square, or if you take it out of the root, it will be root 3F. That is resultant force. Resultant force is F equal to, magnitude of the resultant force is root 3 into, what is F1 or F2 equal to F? K Q square by A square. Okay, this is the magnitude of the resultant force on any one charge due to the remaining two charges. Okay, this is one simplest problem. Another problem we'll see like this. Okay, now this time I'll take a square. This time I'll take a square. Okay, square or a square. Okay, there are three charges, identical charges Q, Q, Q on three corners of a square of side A. There is one side A. Okay, there is one negative charge minus Q, same in magnitude but opposite in sign, minus Q. What is the resultant force acting on this minus Q due to these three forces? Due to these three forces means, call this as corner 1, call this as corner 2, call this as corner 3 and 4. Okay, now what is the force of this charge minus Q because of this charge? Individually we have to see, right? Find the resultant force using vector addition. Okay, first one, force on minus Q due to this Q on charge on corner 1, because these are opposite charges, the force is attractive, it always acts along the line joining them. I'll call that force as F1. Okay, so what is magnitude of F1? F1 equal to K into Q square, Q into Q, Q square. Okay, minus sign will be there because one charge is positive, another charge is negative. Okay, minus Q square by, distance between these two charges is, it is a diagonal, face diagonal of a square. Okay, so if these two sides are A and A, the length of this diagonal will be root 2A, root of A square plus A square. Okay, so it is root 2A whole square it will be. That is minus K Q square by 2A square is the force F1 which will be in this direction. Okay, similarly, force on minus Q due to the second charge on corner 2, right? Again, this is also attraction force. I'll write like this. Okay, right? So this force, I'll call it as F2. Okay, this force I'll call it as F2, right? What is that force? F2 equal to? F2 equal to K into minus Q square by, the distance between these two charges is A only, so it is minus K Q square by A square. Minus K Q square by A square is force F2, right? F2 is acting like this. These two are attracting each other. These two are also attracting each other. These two are also attracting each other. Okay, now the force F4 due to this charge on corner 4 on this charge, okay, we can write it as F4. Okay, F4 equal to, again, right, k into minus q square only, q into minus q square by the distance between, the distance is right, a only, so it is a square. Okay, this is also minus kq square by a square, minus kq square by a square, means this force F4 is like this, F2 is acting like this, F2 is acting like this, F4 is acting like this, and F1 is acting like this. F2 and F4 both are equal, minus kq square by a square, both are equal, and they are having an angle 90 degrees. So what is the resultant of these two equal forces? It will be a bisector of these two forces. The angle bisects the angle between F1, F2 and F4. Okay, the resultant force, angle between these two, F2 and F4, is 90 degrees. Okay, so resultant force I'll call it as F dash. Resultant of F2 and F4 I'll call it as F dash is equal to root of F2 square. F2 square means minus kq square. Let us take this whole thing, minus kq square, etc., whole thing as some x. Okay, so it is x square plus F2 square means x square, okay, x square plus 2 into F2 into F4, that is x square again, cos 90, 0. So simply two perpendicular vectors, root of F1 square, F2 square is the resultant. That is nothing but, right, root 2 x is F dash. F dash is root 2x. Okay, root 2x means what? F dash equal to, okay, root 2 into, right, minus kq square by a square. Okay, now what is the direction of this force? Resultant of direction of two equal forces always bisects the angle between the two vectors. Means this F dash will be in this direction like this. Okay, now this F dash and F both are in the same direction. Simply add them. Direction is same, add the magnitudes. Okay, so resultant force F equal to, right, this force F1 plus F dash. Okay, what is F1? F1 equal to minus K. This is F1, isn't it? Okay. Right? F1 is minus kq square by 2a square. F dash is, right, root 2 minus kq square by a square. Simply we are adding them like this. So minus kq square by 2a square plus, what is F dash? Root 2 of minus kq square by a square. So it is minus kq square by a square. If I take common, it is simply 1 by 2 plus root 2. It is simply 1 by 2 plus root 2. You take LCM, that will be the answer. Okay, this is the resultant force F on that minus q. Now you can, this is the answer. You can take another similar problem, as you can try this at home as an exercise. You can try this. Okay, right, I'll slightly modify the problem here. There is one square. This is our third problem. Okay, you can take this as an exercise. Okay, there are three identical charges Q, Q and Q on the three corners of a square. Okay, there is one charge minus Q at the body center of this square. What is the magnitude of the resultant force acting on this minus Q? Earlier we have found here. Okay, now I am putting the same minus Q charge at the body center, at the center of the square, that's all. Okay, right, what is the resultant force acting on this minus Q due to these three charges? Okay, that you try as an exercise. Now next we'll enter into what is known as electric field in my next video. Okay, thank you.